Hey again everybody, welcome to your second EES tutorial. Today we're going to be working on a simple thermodynamics problem that has to do with grabbing a thermodynamics property given two properties of a substance. And we're also going to be looking at parametric stables and how you can use those to see as a value changes over time, how that changes other values that you're working with. So I'm going to go ahead and start up an EES window that I've already edited for you guys. So here we have a question that I adapted from the Singal-Symbolic-Turner book, The Fundamentals of Thermofluid Sciences, 4th edition. A frictionless piston cylinder device contains 5 pounds of steam at 70 psi and 340 degrees Fahrenheit. Heat is now transferred to the steam until the temperature reaches 400 degrees Fahrenheit. If the piston is not attached to anything, the expansion process is quasi-equilibrium, and the mass is constant. Determine the work done by the steam during this process. Alright, so the first thing that I like to do is write down what I already know. We know that the mass is equal to 5 pounds, and we also know that the constant pressure that we're going to be dealing with is equal to 70 psia. Now, before we do anything else, this is really the first thing we should have done, is check the units. We're working in English units here, pounds, psi, degrees Fahrenheit, and you can see down here that everything is in the SI unit. So go ahead and click on that. We talked about this in the first video. And go ahead and change that to English. Make sure everything lines up, temperatures in Fahrenheit, mass, everything. So everything's great. Click the OK button, and let's move on. So we have the temperature at point 1. Point 1 is going to be before the heat is added, and point 2 is going to be after the heat is added for future reference. So the temperature at point 1, I'm going to say is T underscore 1, and like I said earlier, that's going to come out as T sub 1, and that's for the temperature at point 1, and that's going to equal 340, and the temperature at point 2 is going to be T sub 2 is equal to 400 degrees Celsius. Now the first thing that we're going to do now is write out our equation for boundary work. So W sub B, which is going to be the boundary work, is equal to, it's usually just pressure times the change in volume, but since we're going to be working with specific volumes here, we're going to do the mass times the pressure times the change in specific volume at point 2 and between point 2 and point 1. So we're going to do V sub 2, that's the specific volume after the heat is added, minus the specific volume before the heat was added, and that's going to give us our work. So let me go ahead and show you guys how we can use EES to solve for a property given two other properties of the same substance. First thing we do is go up to Options, going to go into Function Info, Fluid Properties, and you're going to see two columns here. Let's go on the right one and pick out water or steam, and on the left we're going to pick out what value we're looking for. And here we're looking for, sorry about that, here we're looking for volume, specifically the specific volume. And the properties that we have to look at, if you look over here, we have temperature, pressure, and mass. So from this chart, you can see that we can just use temperature and pressure. I'm going to use this example to go ahead and modify the equation. Instead of 1, I'm just going to do an underscore 1, and that's going to go ahead and fix this up so that it matches almost with the equation that I was using for work. Okay, so here we have V sub 1 is equal to the volume, and it has parentheses. The first part denotes what kind of substance you're working with. Here we have water, and the two other parameters that you give it basically tells EES where it's grabbing these other parameters from. So here we have the temperature that it's using is equal to T1, which we give right here, and the pressure that it's using is just going to be equal to P, which we give it up there. So let's do the same thing for V2. We go to Options, Function Info, fluid properties, click on water, got volume, and then we have temperature and pressure. That's correct. Let's go ahead and edit this to say 2, and that's gonna give it to us like that. Same thing as above, it's just using the temperature at 0.2 as opposed to the temperature 0.1, and that's going to give us the specific volume at 0.2. So let's go ahead and solve for this. Let's check it. There's 7 equations and 7 variables. No syntax errors were detected. Perfect. And let's go ahead and solve. We're going to go ahead and ignore the 3 unit problems that were detected, but you can go ahead and see that it gave you the values that you typed in, and also it solved for these values for V1 and V2 and gave you the work. Now then, this answer is incorrect. Let's check units real quick. You can see it says the dimensions of the work and what work is and what the equation for work is are inconsistent. And the reason it's telling you that is because we still need to multiply this entire equation by 1 over 5.404. And that's 1 BTU over 5.404 pressure feet cubed, excuse me. Let's go ahead and solve that again. It's still going to give us the same unit problems, but that is the correct answer. It's 36.46 British thermal units. Alright, so what I want to teach you guys now is how you can use parametric tables to see how changing one variable affects any number of variables that you want to look at. The first thing that you need to do to start a parametric table is come up here to this icon and go ahead and click that. This is going to help you set up your new parametric table. Let's go ahead and rename it something like pressure versus work. So from here, you're going to get the the variables that you had in your equations just like over here on your sheet. And you want to move them over here to the variables that are going to be used in the table. We're going to be looking at pressure. Go ahead and double click to add them, or you can click this to go ahead and add them in. And we're going to do the boundary work. You can also remove one just by doing that. You can also double click to remove. So just go ahead and click OK. You're going to get your parametric table right here. You're going to click on this little smart tag right there, and this is going to allow you to edit how the values of that variable are distributed. So we're going to use 10 rows from 1 to 10. Let's actually increase that to 20. So we're going to be using 20 rows, and for our first value, let's just go ahead and use 70 and see how a pressure increase up to 100 psi will change the boundary work. So go ahead and click OK. It's going to ask you if it's okay to add 10 rows to the parametric table. Say yes. Let's go ahead and expand this so you can see the whole thing. And from here, all you need to do is press this green button, and we have an error. Run 1. P is previously set to a value in the equations window or the diagram window. I'm going to go ahead and show you how to fix this. Just click OK. What it's essentially saying is that EES cannot solve for a bunch of different values of P, since P is already defined in your equation window. So what we're going to do to fix this is simply comment out P is equal to 70. Let's go ahead and check it. 6 equations and 7 variables. So that's actually what we want in this case. Let's go ahead and press play, and there you go. All of the values and how they change depending on how the pressure changes. You can see that the work increases as the pressure increases, and intuitively that's exactly what would happen if you're looking at the equation. So let's go ahead and make another parametric table where you can look at specific volume 1 and specific volume 2, as well as the work and how those change when pressure changes. So we're going to add pressure, we're going to add boundary work, V1, and also V2. Click OK. You can see that it added the other two here. And let's go ahead and do something a little bit different with the pressure. We're still going to be using 20 rows, so increase that to 20. But instead of doing a linear fit in between 70 and 100, we're actually going to increment the values by 2 from the number 70. So this doesn't have like a top limit, it's just increasing 2 from row 1 to 20 for every time after the value 70. Go ahead and click OK and yes to confirm that you want to add 10 rows to the parametric table. And let's go ahead and expand this again so you can see everything. And here you can see 70, 72, 74. It's incrementing by a positive 2 every time. So let's go ahead and run it. And there you go. Here it's going to give you all the values for boundary work, all the values for a specific volume before the heat addition and after the heat addition, all depending on a certain value of P. And it shows you how that increases as these increase also. And this makes sense, you know, as before, the work increased as the pressure increased, but you can also see that as pressure increases, the specific volume decreases, which makes sense. Alright guys, thanks for watching, and I'll catch you next video.